but there are certain points in the slideshow where we'll pause and say, please ask questions via text chat. And we have many teachers here who will read the text chat and look for questions that we can pose to Ms. Pueyo. I'll call you Dr. Pueyo.
Not yet.
Yeah, sorry, not yet, but it sounds better, right? So you can ask questions of Dr. Pueyo through the text chat. We have many teachers here. We'll be searching through it. We'll ask your question. We'll try to give you credit for your question. So if it is Josiah Olson who's asked a good question, we'll say, Josiah has a question. And we can't answer an infinite number of questions, so we teachers are kind of sorting through and choosing the ones we like the best. And there will be, I believe, 4 different points during the webinar where you can ask those questions. So please be thoughtful. And the questions do make it a much better presentation. So please don't be shy, ask your questions, and we will present them to Dr. Pueyo. All right, are you ready, Dr. Pueyo?
I'm ready.
Okay, let us, I'm going to mute myself so that I don't get in your way, and I just have to remember to, I have to remember to unmute myself when it's time to talk to the students and ask questions.
Okay, so good morning, everyone. My name's Natalie Pueyo, and I am going to be talking about the 2 projects I've been working on during the last 3 years. So first, a little bit about me. This is kind of a bit of like the resume of mine, but I think what's important here is that I was part of Laguna Beach, and because of that, I was able to be an ACR, and that really showed me that I loved research. At the time, I thought that it was that I loved chemistry, but there were some things that showed me that what I really wanted to do was something more hands-on and something that I could like build myself. And part of that was AP Physics with the cardboard boats. And part of that was that once in school, I took an engineering introductory course, and that really like helped figure out what it was that I wanted. But even now, I'm still not sure what I want. I graduated with mechanical engineering, but once I went to work, I found out that I hated doing typical mechanical engineer stuff. Even though I had my own project and it was like this really cool like starting job, I didn't like it. And so I decided to go back for my PhD to go into precision agricultural equipment, which is a combination of a lot of things. There is mechanical engineering, but I've also started looking at electrical engineering. I have computer science, and I'm even going into like mathematics right now, which is something I never expected but have really come to love. Right now, you can see the picture in the bottom is the piece of equipment that I redesigned during the 1.5 years that I worked in industry. And I did pretty much all of that. So it was really cool. And if anyone has a chance to go and do internships, I highly recommend them because they helped lead me to all these things. So what are the projects I'm going to be talking about? The first one has to deal with these like strawberry carritos. They're these tools that they use in the field to carry around the big boxes of strawberries when they pick them. And each picker uses their own. So our project will have to deal with constraints like they have to be lightweight for transportation. They have to be cheap and simple because they have to get their own carts and stuff like that. And so the project that we had was to redesign or design a piece that would go onto these carritos, and it would have sensors that would be used to get data that we would send to a robot at first, and then when it evolved into another project, we also had to be able to send it to a computer for post-processing. And the idea of this system is that it connects GPS data with weight data, puts it together, and then use that for research. Now, why would I work on strawberries? This is something that I've been asked a lot, because a lot of people who don't have agricultural experience don't know that it's a huge industry and there's a lot in it. For example, UC system collects $6.9 million in just 5 strawberry patents. And so, and actually in Davis, it is one of the largest incomes to the university. And so you have these really big systems that not a lot of people work on, and they're very, very complex. And so strawberry research is labor intensive. You need a lot of people working in the fields because they're all picked by hand. There's no automation right now. And these tests can run on hundreds of plants over months or over multiple years. Usually you can see in my screen, the normal process that they use right now is that they'll do research on blocks of plants and they'll get data on that block. However, it's very coarse because they don't know which plant did what. And there's a lot of error as well, because if they mislabeled something or if there was a problem because a storm killed half the plants, they lose all that block. So the idea right now with our card is that because it's linking the weight data with the GPS data in real time, they can get the information on each plant rather than on a whole block. And so we're hoping that that'll help decrease error and increase the amount of information that they have. And so we have the system overview right now is that we have the sensors. They do go through some corrections with the sensors. And then what we really want is this data, the strawberry weight and the latitude and longitude from the GPS, so that we can put it all together. And then once we have that, we can either put it in an SD card so that we can save that, and then either Bluetooth it or communicate it to whatever system we're interested in. This can then be analyzed in a computer or something like that to make it even better. And so this is our first generation. I actually inherited this project. This was already existing. You can see the Carrito is this black part, this triangle, and then the system that they built was right there. And you can see that it's welded right there. The mounting is a little bit complicated. You have all the wires, you have a bunch of electronics, but it worked. And this is how you put the card and you carry it around. But it also had problems. And so one of them would be that the wires are out in the open. And so when the pickers are out, so when they're out picking, this could be a big problem. There's also badly mounted sensors, and it's very hard to build because all the parts are different. Also, it's not very robust. If someone kicks it, it could break very easily. There wasn't enough documentation to really be able to replicate it. I couldn't copy all of it because maybe that piece was missing or the electronic part doesn't exist anymore. It's also hard to build more copies because of all these different things. And we found out that some of the sensors were having issues. Do you want to stop for questions here?
Yep, this is a great place. So we're going to pause here. And we're monitoring the text chat to look for questions about anything you've seen so far in the presentation, or more general questions are also valuable.
That's right.
I'll ask the first question here while we're waiting for students to put things in the chat. So what I'm looking at on screen, it looks to me like it's copper plumbing tubing. What is that actually made of?
So I believe this was steel tubing. Some of it is just filled in tubing. The other stuff is, the other stuff is just, some of it's solid, some of it's not. They just grab pieces from the shop and put it together as they could.
Yeah, that's what it looks like. It looks like kind of a Franken, let's grab some pieces and put them together and see what happens, which is maybe good for the first generation.
Yeah, no, it showed us a way that we could move forward. Like it showed that the two sensors, two weight sensors were good enough. And that maybe this is a configuration that works. So in that case, it was an incredibly useful piece.
Okay, here's our first question from the audience. It's asking the word carrito. Where does that come from? What does it mean?
So most of the pickers, if not all of them, are Latin American. And so they've taken the word cart and added the ito, the ITO, which is a diminutive. So what they're saying is it's the little cart.
Okay, here's the next question. And this may be what you're going to get into next. So don't feel that you need to answer it if you're saying, I'm just about to get to that. But the question is, what hardware do you have to communicate the GPS and weight sensors?
So I will get to that. But the main computing power is done through an Arduino.
Arduino, obvious. Excellent, excellent. Okay, next question. Is this to see which strawberries grow the best?
It can be. So there's multiple types of strawberry research. Some of it is if they're breeding a new variety, they want to know how well it does. And so they can use the Carrito to figure out if that variety is growing better, or it grows bigger strawberries, or it grows more strawberries. So it can use that to figure it out. There's also things like testing for fertilizers or if pesticides do affect it. And so all of that is based on, say, how many strawberries they can get out of the field. Because if the pesticide's killing the plants as well, then you get no strawberries.
Okay, I forgot to give credit for these questions. So the first question was from Anna Chang, and Kenneth Chu asked the hardware question, and Nicole Brown asked the big picture question, what's the real purpose of this? All right, and we now have a question from Kyle Herkins, and I'll read it verbatim and maybe we'll paraphrase, but he says, so this is the machinery, but you can set it to measure different things based on what sensors and coding you use, question mark?
Yes. It's a very general question.
Yeah, so, but I think you're going to get into what kind of sensors you put into it, and maybe that's a good time when we can say, are there other sensors? I think, yeah, so maybe we'll get to that in a little bit, Kyle. It's a great question about what can you measure, and which of those are dependent on the hardware, the sensors, which goes back to Kenneth's question, and then there's also the software. The coding will determine some of the things that you can measure. All right, perfect. Great questions. Thank you. We'll go back now and let Dr. Pueyo continue with some more slides, and then we'll have another pause for questions after that.
But yeah, no, thank you for the questions. I enjoy this. So then we have the Carrito, but we also have the problems that it comes with. And so the next part is, what do we do? And so the idea was we needed new specifications. For example, one of the really big things is we needed to make it more robust. If it breaks in the field, there's nothing we can do. We need to make it more modular so that everything fits together. There's changes made constantly. I went through multiple generations and multiple iterations. And so everything needs to be able to change, but also fit together. And we also needed to add sensors, which from the previous question. And then the other thing is we needed to make it easier and faster to assemble. Welding is a very, very specialized ability, I guess, technical ability. And so we wanted something where if we give someone the parts, they can just put it together, especially because we needed to build 25 or more of these cards for the research project. And we also wanted to try and make it more resistant to water leaks, because in strawberry country, there's a lot of fog and rain. And so if water gets into the electronics, they can break. So then we changed our manufacturing process to meet these specifications. For example, we decided to go with sheet metal. And so that includes laser cutting it, bending it. And we also needed to print some parts, so 3D printing. And to make it even more resistant to punishment, let's call it, we also worked on creating a circuit board where all the electronics would come together. So what is sheet metal? Sheet metal is these really thin pieces of metal, obviously, in this case aluminum, and they come in these giant sheets. They can be like 16 by 4 feet or stuff like that. You buy them at the sizes that you want, and usually it's relatively cheap because it's easy to manufacture. It has low weight because it's so thin. It's a forgiving material. I made a lot of mistakes and mostly it went well. From my work, I already had experience designing sheet metal parts. Some of the parts in the big machine in the introductory page were actually sheet metal. And then we chose aluminum because it wouldn't rust in the weather. And if mud got on it, it was fine. And so you can see here would be some parts that haven't been bent, while this part has, or this one as well. So to work on sheet metal, we decided to start with 3D modeling, which is the way most everyone in industry will do it. I use Autodesk Inventor if people are interested in this kind of stuff. This is free for students once you get your .edu email address. You can sign up and get a free version of it. So this is what's called a 3D modeling CAD program. And it is a computer assist design program. So it helps you build it in such a way that it's easy enough, and whatever you imagine you can put onto it. It was used to design both the sheet metal parts and the 3D printed parts, but it can be used for a lot more stuff. And what it does is that it helps us fit everything together before we build it to make the process a lot cheaper and easier. Because otherwise we would have to like do it by hand and put it together, and if it doesn't fit, we have to redo the parts. In this case, we can figure out all these measurements beforehand. And so this is kind of the process of what we do. It starts over here where I built the 3D model. You can see where I wanted each bend. I knew the lengths and locations of everything. And so once that was done, the program, the inventor, was able to take it and make a flat and flatten it out. And so these yellow lines that are a little hard to see show where the bends are going to have where the bends are. And then this is taken and you make a drawing out of it. And you can see here it is folded and here it's the flat sheet. And so once you have that, you can give it to anyone who knows how to bend sheet metal, in this case me. And so they can figure out where the bends have to be and how much they have to bend the parts. And so, but before we bend it, you can take these drawings and you put them all on this giant sheet, and you figure out how many you can fit in this sheet of metal so that you can print it out. And so here's a video of the process of, laser cutting. And the sheet of metal that I was using was about that thickness. You can also see how precise it is, which helps a lot when you're trying to make parts that have to fit together. And so we wanted to I keep saying print out. We wanted to cut out 5 of each carrito so we can start building them in groups of 5. And you can see what that would look like right there. So next, after you have the pieces cut out, you can then go into sheet metal bending. This is a automated way of, this particular video shows it's automated, but you can see the process. It seems very easy, but what it really looks like in the shop is something like this, where you have this giant piece of equipment and you have to go in, fit it correctly, you lock it into place, and then you use the machine to bend the piece of metal. What this video doesn't show you is that it's very error prone if you've never done it. And it also doesn't measure what angle it's going to. So you have to stop constantly and check that you're at the right angle, move it a little bit. Sometimes it won't lock into place, so you have to tighten it. And so you're doing this constantly. But it is a ton of fun. And the shop is a really, really cool place. So once all the bending is done, you go from a piece like this, where you can see the drawings, the flat pieces, to the full-on carrito. So it's a really, really cool progression that you can go through manufacturing the pieces. Next, we had to do 3D printing. Sheet metal is incredibly flexible, but there's only so much you can do with it. You need to be very careful about where you put all the bends, and you can't just put, it can't be very complicated. So we use 3D printing to make more complicated parts that we couldn't manufacture otherwise. One of those examples is this box. You can see that this box is for electronics, so I would put boards in there. You can see that right there. And there was no way we could manufacture this without 3D printing. Other pieces are very simple and fast to print out, which was like this insulator. And so 3D printing is very helpful in that sense, where you need something that's pretty complicated, that 3D printing can still do, but also something that's fast, because one of these boxes and a few of these little insulators would take something like 8 to 12 hours. And just because I find it hypnotizing, here's a video of 3D printing happening in real. And you can see how it like builds layer over layer slowly to create these really, really cool and very complicated pieces that you can't manufacture otherwise.
Okay, great. So let's pause now for, again, looking for student questions. Okay, here's the first question from Ben Keller. How has coronavirus affected your project?
I've actually finished working on this project, which was very hands-on, and moved on to a different project, which I can do from home. So for me, it hasn't actually changed that much in terms of research, but for the people who inherited this project from me, it made it a lot more difficult to be able to build the 30 carritos that they needed to build.
Okay, here's the next question from Nicole Brown. How long did it take to make each machine or each part?
So it varies. The first time around, it took a really long time. I believe it took about a year to kind of make the design and then to start making the parts. And for example, the first time I tried bending the metal, I had the wrong kind of metal and I cracked every single part. And so that just made it take so much longer. I think it was by the 1.5 year mark that I actually started being able to build parts very easily. And it got to the point where we could make all the parts, all the bent parts in 5 hours for the 30 carts.
Oh, wow, that's pretty good. So 5 hours for 30 carts. And then after they're bent, then you manually assemble those bent parts?
Mm-hmm. So all the bent parts, if you look at the so you can see like in this one, we have holes where you mount them. Everything was connected by screws and nuts and bolts to make it as easy as possible to replace parts. Yeah, and you can see some of the screws right there.
I'll ask the other teachers to think of questions while we wait for student questions as well. This, I think, is Luca Elganian. What was the most difficult part of the manufacturing process?
Usually it's the start. So because you have very little to go on, you have to design a whole piece of equipment. Just starting is very difficult because you don't know what the measurements are, you don't know exactly what you want it to look like, and taking measurements is very difficult for something with so many angles. So it took me a while to start figuring out what I wanted to create.
Question from Kenneth Jew. How much does it cost to manufacture one cart?
I'd have to open up the bill of materials, but with with all this electronics, etc., it was about $1,000.
For each
Just
cart?
yeah,
Okay.
just because as I'm going to talk about later, some of the electronics got very expensive.
Okay, great. So you'll be talking about that. Question from Mrs. Perkins. Are these devices in use today?
Two of them are. The ones being built, not quite, but they're planned to be used during summer if coronavirus stops, is to do some picking already. Yeah, because there's two different projects. The first one with a robot just needed around 5 of the cards. The second research project actually needed the 20 or 25 cards so that they can actually have pickers out on the field collecting data.
Okay, we have another question from Sydney Wook. Do you make money off the machines? This is actually an interesting question to think about.
So academia is interesting. We're making money for the machines because it's included in a grant. So for the research cards, what happened is another professor got a very comprehensive grant for strawberry research, and they decided that they wanted our cards for this research. And so they went and talked to the professor I work under and were like, look, we have this grant, this portion will go into making these cards. So we don't sell them, but we do make money through the grant process to build them.
Yeah, so I'll add on to that. Are there things here that you could patent and then have it be a source of revenue for the university?
Not as, I don't think we could patent it. The idea isn't quite novel enough. We're putting a lot of stuff together that already exists. But you could try to be first to market with something like this and try and make some money. But it's a very, very specialized tool. And until it becomes more widespread, and if it becomes more widespread in other areas like other crops, I don't think you could make that much money.
Okay. And here's a question from Theo Coffee. Has a type of Carrito with this kind of technology already been built, or is this the first technology-based Carrito?
For strawberry, it's never been done before, which surprised me, but it is what it is.
Okay, excellent. So you're the Pathfinder. Okay, I think that's a good point for us to go back to allowing you to continue with your slides. Thank you for the questions. Mm-hmm. We'll have another break in a few minutes.
Perfect. Okay. So 3D printing. Okay, so with the end of 3D printing was the mostly end of the manufacturing process. And so we started focusing more on the electronics. To do so, we needed a smarter carrito. So we needed a more powerful computing. So instead of moving to a completely different microcontroller system, which would be complicated, we tried to find a more powerful Arduino, which ended up being the Duet. We tried to find weight sensors with better mounting because in the previous iteration, it had only 2 holes to mount, and so it wiggled a lot. And so the idea now was to have one with 2 mounting holes in each side, and so it would wiggle less because it's held on. We needed some kind of communication system. We began with LoRa, which is long-ranged wireless communication. But for the research ones, it's going to be Bluetooth because they don't need long range. Then we needed to switch an accelerometer, which is a type of sensor, because the one that they had put in the original cart, we can't find it anymore. Like, it can't be bought. So we needed to find a new one. And then we also wanted something where we would have power for around 8 hours or more. And so we needed a new battery pack and all the electronics that support that. And we also decided that we wanted some kind of user interface. So in this case, buttons and LEDs, so that it'd be easier to work with the Carrito in the field. So maybe the researchers want to download the information, they push the button instead of having to go in and like put in special code into the Arduino to do it. And so we needed all these things that the older cart didn't have. And at this point, we also find that our biggest problem was that the GPS that was in the original Carrito was not good enough. It had an accuracy of 5 meters, and that's huge. You know how your phone GPSs, when you're driving, will be like, oh, you didn't take the exit that you actually did take? That's because your GPSs have this type of 5-meter accuracy. And they can fix it once they know you're moving, but our system is in very small spaces. And so we needed a less than 1 meter accuracy GPS. And so what we found out was that the strawberry beds are around 0.6 meters apart. And so that's what we determined would not have to be our maximum accuracy. So we could actually tell when they're in the furrows and in which furrow they're at. And we had 2 technologies that we were looking into to see if this was possible. So the first one is RTK GPS. It's an already well-known GPS technology. It's got centimeter accuracy, so it's really, really good, but it has 2 problems, really big problems. It needs a second station that's stationary, so that it uses that second station for corrections. And the problem with that is that when you're working with strawberries, the pickers move from field to field all day. And the second station, if it need, as you get further from it, the error increases. And so having a stationary second station wouldn't work very well. The other thing is that RTK GPS is incredibly expensive, and because you need 2 stations, it just becomes even more expensive. And so what we ended up doing was we went for a second and newer technology, which is SPAS GPS, which has some meter accuracy, but because it's newer, we had no idea if it would work for what we wanted. But what's cool about this one, it's a lot cheaper, and it didn't need that second station. So the test to see if the new GPS would work was we took these points, the blue ones and the red ones, with RTK GPS because it's so accurate. And so we knew where each furrow was. And so we connected that, and so you can see this is where we should be walking, or this is where the signal should be to show that the Carrito is in a specific furrow. And then we labeled each furrow with a number so we would know exactly which furrow we were in every single time. And this was really important because when we actually did the test, we found out that our accuracy was correct. Like, it was within the parameters we wanted, where it's 0.5 and about 0.5, which is less than the 0.6 that we wanted. But we also found this thing that's called a bias, where the data was moved over, and all of it was shifted. That's what I'm trying to say. And we found out that this was not related to time or location because we tested in different fields, and we also tested at different times of the day. So what we figured out was that the RTK stations that we were using were based on a 2010 model. And this was really important because the base that we were using was a tower in the, the model was based on a tower in the Salinas Valley, which is right on top of the San Andreas Fault. And so you have a lot of tectonic shifts in near the San Andreas Fault. And so the 2010 model didn't take into account these movements. And so you have this error. And apparently in the last 10 years, the error was about 2 meters north and 1 meter east. And if you want to better look at what bias might look like, the shift, you have this scenario where it kind of looks like they're in the correct position, but because we knew by numbering the furrows that we were in, we knew that this was wrong. So you could just shift it over to something like this. Same here. So we have the morning and then we have the afternoon. Yeah. And I think that's a stop.
Stay there for a second, Natalie. So you're saying that you know which furrow you walked.
Mm-hmm.
And you're saying the bias example, that wasn't where you were walking.
Mm-mm.
But you
No.
corrected it by shifting everything over a couple meters. And then you said the no bias, what you're presenting as no bias is that matches what you actually did. So you know that is accurate data. Is that what you're saying?
That's exactly what I'm trying to say, yes.
Perfect. Okay. And then it looks really nice. You walked down that furrow right there.
Mm-hmm.
And you walked on the yellow one, and you walked on the green one, you walked on the red one. Okay, perfect.
Exactly.
Thank you.
I also think this was a stopping point for questions.
Okay, great. Then once again, we'll look at the chat and see what questions you have. Okay, here's an interesting question. It's from Luca Elganian. And he's wondering, could you build a system that didn't have the GPS, but that had some kind of user interface? He's saying maybe buttons for the pickers to press to tell the Carrito when they're shifting to a different patch.
Technically you could, but it would never be able to give you the information that you want. Because we're not only looking at the furrow they're in, we want to know where in the furrow they're at. So just being able to tell what furrow you're in or what patch you're at would not give you the location data necessary to get the data that the researchers and the robot require.
Okay, so you're looking for very fine data, not just saying it was the yellow line, but where exactly on the yellow line were these strawberries picked, huh?
Yeah, so for example, with the robot, the picker might be in the middle, and so the robot needs to know that it has to stop before it gets to the picker. But the other thing about this robot is that it needs to know to which picker it's going to go. And if the data is not fine enough, if it doesn't know exactly where the pickers are, its ability to figure out which picker to go to is going to be bad because it doesn't know how far away it has to walk. So it's going to maybe prefer to go to someone closer, or let's say someone further away. But it has to know that it has to go that distance. I don't think I'm explaining it quite well.
Talk a little more about this robot.
So this robot is a robot that is assisting the pickers. It's the idea behind it. As the pickers get all the fruit, they fill out these big cartons. And the idea behind this is that if we can have a robot pick up the large cartons once they're full, it'll help increase the rate of strawberry picking, because at this point the pickers don't have to go drop off these large cartons to a weight station.
Okay, so that's really interesting. So then you're saying the the Carrito is sending information constantly. So perhaps many Carritos are sending
Mhm.
information to the robot. The robot has to take that and say, this one is going to be filled very soon. I'm here, he's there. I'm going to go there and I'll be there in 25 seconds.
Mhm.
And presumably the robot has very big capacity, so it can take lots and lots of boxes of strawberries, but it has
So,
to plan the
mm,
most efficient route. Okay, very
yeah.
interesting.
And because and the question isn't always like between one person who's almost full. The idea is if there's two people who are almost full, which one does the robot go to? And unless the robot has a very specific knowledge of where the pickers are, it can't decide which one to go to first. So that's why, in that sense, we needed very specific data. In the researcher's case, they want to know very specifically which plants are having issues and which ones are not. And they can aggregate this data um, and put it together and then figure out if their treatment is working or not. But they want this to be as specific as possible.
Excellent. All right, we have a question from Mr. Myers. And he's talking about, because tectonic activity is always happening, how will you account for that movement in the future?
Uh, that's a good question. So tectonic activity does always happen, but it's slow enough that we would be able to update it maybe once a year and that would be it. In this case, it was 2 meters in 10 years. So as long as we know and we constantly keep going every year to like correct and figure out exactly where the bias is, I think that would be good enough.
All right, excellent. Okay, let's let you continue with your slides. Thank you for the questions.
Okay, so once we finished doing this look into the GPS technology, we were able to tell that we could see which furrows we were in, and that was good enough for us to move on to the next part. Um, and so that would be designing the circuit around the Arduino, the sensors, and the new GPS. And so to go through that, you start with a very basic just hand drawing, just to figure out how everything fits together and what connections are there. Um, Once you have that, you can then use a different CAD program. So CAD is computer aided design program. So you have a multitude of things and they're all very specific to what they're doing. In this case, Eagle is for electrical circuits. And so what Eagle does is it has a schematic and a board. And so you translate your circuit into a schematic, and that's where all the connections are between your electronics and electrical systems. Um, and then once you have that, it links you to what's called a circuit board, where you know the sizes of all your parts, and you can figure out how to put them together. In this case, we were limited in space, so this was very helpful. I knew I had a specific space, and so I was able to fit everything very closely. The other thing that you're doing when going from a circuit schematic to a circuit board is that you then have to draw the connections between all the parts. These yellow lines that you see, those are the connections between parts. The red lines and the blue lines are already existing connections that I've already made. And so I just needed to put more of those to connect, say, this little part with the part over here. And that's kind of how you end up building a circuit board. Once you connect everything, you end up with something that might look more like this. It's a finalized board. You can see this would be like the Arduino right here. I have a GPS right there. Here's a module. There's another module for the load sensors. And these are all where I can connect wires to maybe the batteries up here, button and LEDs were down here. And so you can kind of see how it's all interconnected. Once you have that, you send it to a manufacturer and you get these green boards or whatever color you want. but they're not populated. You don't have any pieces on them. They're just these connections that you made on the CAD program. And so you have to go in and populate the board. And here you can see the GPS, the Arduino, and all these connections. And you can also see the battery back there. So that's how the circuit was done. And so at that point, we had pretty much all the parts. And so we go back to this first generation showing what it would look like with the electronics. You have the weight sensors, you have the mounting points. And then this is the second generation where it's all a lot more put together. It looks like something you would take to the field, and that could take some punishment. You can see we now have a GPS antenna mount because we needed to make sure that the GPS was as accurate as possible. Easier mounting, we have the user interface, and so you have all this more, it's ready now to be able to go to the field. And so that was the end of the project for me. I ended up building 2 of the Carritos plus the parts for the 20 or so more. And I handed it off to a lab mate who at this point is already making a new version of the circuit board. It's been moving very quickly where more stuff is added, more stuff is added. In this case, I think they're adding the Bluetooth and the ability to connect 2 more weight sensors. But they said that it was incredibly easy once they had the parts to just put it all together, which was something we were really looking for. And then I also recently found out that it might be expanding into, say, table grape research, soon to take over the world. So that's really cool that something can keep going and evolve into something like that. And then for me, it was actually, I was really excited that it ended successfully, but I'm also really excited to learn something new because it took me 2 years of just trying over and over and over again to get this to work. And then so when it finally ended up working, I was like, okay, I'm done, ready to move on. Yeah, is this a stopping point or keep going?
Okay, I think in the interest of time, because we're at 12 o'clock
okay.
now, that will let you go on to your last few slides, which talk about your new project.
Okay.
But we'll just kind of go through that fairly quickly.
That works.
And then we'll pause at the end for people to ask questions.
Okay, sounds good. So once I finished this project, I went to the next one. The idea is it's an orchard fruit picking robot, and I'll be working on this for the next 3 to 5 years. And the idea behind it is that there's been 30 years of research into automated fruit picking, but it's never actually worked. There were 2 main problems. The first one is that inside a tree, it's very hard for the robot to find the fruit and to reach it because it's very complicated. You have the branches, you have the leaves, and computer vision systems weren't good enough to really tell leaf fruit. The other problem is that it's too slow compared to human pickers. I think people can do 1 fruit per second, and the robots were never able to do that. And so instead of looking to technology, they started looking into changing how the trees grew. And so breeders started training their apple trees to look something like this, where it's just flat. It's like a wall of fruit. And you can see that it's a lot easier to see the fruit and to reach it. So that solved that particular problem. And so it's created a lot of new interest into, can we build an automated picker? Especially because labor has actually become a lot more expensive, such that a lot of orchards can't pay for it and are switching to other crops. And so our question was, okay, now that we have the seeing and reaching kind of solved, how do we make it faster? And can using a lot of very cheap arms at the same time all picking together solve this problem? And so we are going to be working on this, but there's also 2 companies that have already started working on it as well, who are trying to commercialize it. And so the idea for us then is to create this simulator that can be used to develop the robots, because it's very expensive and error prone to just start building something. And to be able to test many variables like, what if I use more arms? What if I put the arms all one on top of the other? What if so like you can change it. And with a simulator, it's fairly easy and cheap to do that. The other thing is that we can make this available to, say, these two companies or to anyone else who might be interested in creating who's tackling this problem and who might need a way to test stuff, but they don't want to put the resources into creating a whole simulator. And here's a video of the two companies, what they're doing. So this one's trying to do something where they have multiple arms. This was our original idea, and they're very simple. Like, they don't like bend or anything. They just extend, move up, down, left, right, and they can get the fruit. The other company has a different idea. Instead of using grippers, they are using like a vacuum. And so it's just a vacuum cleaner that comes in, sucks out the fruit, and it's actually a fairly fantastic way of doing it, because the fruit gets less damaged, and that's what you're looking for when harvesting fruit. What's really funny, though, is that the first company that's using a lot of arms, they patented that idea where they have a lot of arms in one setting. So the ones that are using the vacuum cleaner can't actually do that. They can only have one at a time. But yeah, so the simulator that I'm developing, it's going to be in Python. It's a programming language. And the idea behind that is that it has a really large community. So any question I have is probably already answered on how to do certain things. While it also has comprehensive math libraries, which are really important in simulation because it's all math. And so this makes it very easy for me just to focus on the simulator itself rather than dealing with the programming. And then the idea behind the simulator is that you have let's call it a loop, and each loop is a step of time. So in this case, it's 0.01 milliseconds. And so you set your desired variables, 30 arms, all on top of each other. They move this fast. And then the vehicle moves as much as it would in 0.01 milliseconds. Then it figures out what fruit it can see, and if there are free arms over here, it'll give those arms goals as a fruit. So it's like, this arm is going to go to that fruit, and this arm will go to this fruit. And so if there are no arms, then it just skips that step, and then all the arms move as much as they would in 0.01 milliseconds towards the goal that they were given. And this just loops around over and over and over again until you reach the end of the row, or you picked a whole tree, or depends what your end criteria is. And so that's a very basic view of that. But this is what it might look like, or this is what it looks like right now in action. So you can see the arms extending towards the fruit, and all the fruit that get darker are the ones that have been picked. And so you can see that this one's moving up, and then it moves over. And we can use that to then be like, okay, this is what 12 arm looks like. What if we added 3 more arms? Or what if we made them slower or faster? And we can do that very easily and very quickly. And then once the simulator works the way we want it to, and we prove that it works, next is looking into how to actually assign what arm goes to what fruit. It is not a solved problem, which is why that's what my research will actually be going into. And it might seem like very trivial. It's like, oh, just go to the next fruit. But what we found out is it's not that easy. For example, I was trying to increase just the speed of the arms to go faster, faster, faster. And what I found out was that, yes, like the amount of fruit that is picked does go up, but at some point it starts dropping. And I couldn't figure out why until I found out that the reason it was doing this was because the fruits in the back and the middle of the machine picked all the fruit they could. And then the front arms had picked most of what they could, but they still had fruit coming in because the vehicle's moving forward. And so the fruit in the back and the middle had stopped working completely, and only the fruit in the front were picking apples. And so that slowed down a lot how fast the machine could pick apples. If the arms were always picking, and that's called, if I balance the load on all the arms, then they would be able to pick faster, even though they move more slowly. But anyways, that's my presentation. Thank you so much for listening and for the questions.
Okay, wonderful. Thank you, Dr. Pueyo. And now we can go to the chat and look and see what we've got for questions. Chat. Okay, here's a question from Sylvie Libert. Talking about the Carritos being in the sun, would it be possible to use solar batteries so that you wouldn't have to charge them as often?
Not really, because if you look at this one, even though it's slightly different from the final version, you can still see that the box for the strawberries is like taking up all the space. And solar powered cells right now are fairly slow, so it wouldn't be able to charge when the box is not on there fast enough.
Okay, we have a question from, it's actually a little discussion here, talking about, are you considering the idea of robots taking people's jobs away?
Yes, that's something that I'm gonna have to deal with for the rest of my life if I work in robotics. In this particular case, we are already seeing that there's not enough labor for agriculture. The people who are in ag, the pickers are, I think the median age is now 50. And so no one wants to take over the jobs, and you're not getting enough immigration anymore that brings in new labor, because in Mexico, the situation is getting better. It's becoming more industrialized. And so you have less people wanting to come. You also have the fact that the border is being a lot more, you have a lot more, they're controlling the border a lot more, so less people can come through that way. And so as the population of the pickers gets older and no one takes over, what do you do? And in a lot of places, they've been, in Napa, they're being paid $20 an hour or more now to pick the grapes. The problem with that is that people who are not used to the labor will try to come in and pick the fruit, but a lot of them won't stick around because it's such backbreaking work. And so less and less people are doing the work, and so the prices are increasing.
Okay, good. Thank you for that.
Sorry.
We'll do 2 more questions from the list, and then we'll say this webinar is complete. So here's one from Mr. Duong. So what new mathematics did you have to learn to help develop the algorithm for fruit picking robots?
I am learning those right now, and it's, the mathematics are, there's optimization, which in a lot of ways uses calculus, but it is a complete branch of, if you have these constraints and you want, let's say, to minimize time or minimize distance, how can you figure out what the solution is to minimize whatever you're trying to look to minimize? And it has a huge amount of its theories. There's multiple ways of algorithms, heuristics, but it's not a very easy problem yet, especially for discrete. And then the other thing that I'm looking into right now is called scheduling, and it's a type of optimization But the idea is if you have these resources and you're trying to do these tasks, how do you assign each resource to a task? Also not solved yet for
Okay,
this
excellent.
particular thing.
Yeah, that, if Kenneth, you're still there, that reminds me of what you were doing last summer, or last year, I guess it was last year, trying to figure out if we have these human resources, these people, how do we schedule them so that work actually gets done and the project can proceed. All right, this will be our last question. It's from Taro, and it says, is it possible for the grippers to squeeze too hard on the fruit?
Oh yeah, that's a huge problem. Grippers are a whole research problem in and of themselves. My work is actually has like a, we are going to ignore the gripper completely.
Okay, very good. All right, then let us say this webinar is now complete. If you would like to stay on, some of you like Cole Hunt, I'd love it if you stayed on, you alumni, and maybe give us a brief update. But we'll thank you all for being here. We'll have another webinar like this next week. And I hope you take advantage of this opportunity to learn some new things. All right,
Thank you
very much.
Thank you, Mr. Sogo.
Thank you.
Thank you all.